All right, let's go quick review style. Quick review style says we have totally proper integrals, we can do those. We have somewhat improper integrals that have a cusp. We can split it up, do those. We have something that blows up in the middle. We can attempt to integrate improperly if we go from this side and from this side. As long as both sides converge, the whole thing converges. All right, so we're okay with that. But if one side or the other diverges, both of them diverge, whole thing's a wash. In this case, as we have something that blows up to the right, what we're going to do is we're going to replace the problematic part with a limit, and we're going to see whether the integral converges or diverges. If it converges to a finite value, then we have an integral. If it diverges to an infinite value, then we're going to have divergent no integral. In this case, same thing happens to the left. So now, what are we down to? We are down to where? We have, instead of something that's blowing up one place or the other, we're actually going to go to infinity, where one of our limits is infinity, either positively or negatively. That's where we're at now. That brings us to this next problem, 7.5. It's the same function that we've used already. We used it way back here, and we said, hey, 1 over square root of x from 0 to 1 dx. We go this way, we say, hey, it converged. Even though it blew up on this side, it converged. But that was only from 0 to 1. Now let's go the rest of the way. So instead of dealing with this component, that's not what we're going to work with. What we're going to do is we're going to work with this side over here. Now, the good news is, as x approaches positive infinity, y is going to be approaching 0. What's nice about that is I'm going to be adding less and less and less as I get out here. So for all intents and purposes, we would think that if I add all this up to, say, about here, wouldn't that basically be enough of an integral to say, hey, the area underneath that integral is pretty good to go? Don't know. That's what we're going to find out. Here we go. We're going to say, all right, same rules apply. 1 is no problem for me, 1 over root x dx. However, this whole infinity jazz, I'm not sure about that. That doesn't look like a valid bound, so I'm going to replace that with r. And I'm going to take the limit as r approaches infinity. Now, of course, we don't need to do left to right, because if we're approaching positive infinity, you can only approach it from one direction. Not the band, just the direction. Now, in this case, we're going to rewrite this limit, and we're going to say the limit as r approaches infinity from 1 to r. And we're going to say x to the negative 1/2 dx. We're going to integrate that. We're going to say the limit as r approaches infinity of 2x to the 1/2 power found at 1 and r. Okay, so let's go ahead and take that and plug that in. So we're going to go right back here. And we're going to say 2r to the 1/2 minus 1 to the 1/2. And of course, the whole thing as the limit as r approaches infinity. Don't care about it here. I'm going to end up with a very nice little -2. In this case, I'm going to come up with a square root of infinity. So if I have infinity and I take the square root of it, well, the problem with the square root of infinity is that it is still infinity. So I end up with infinity minus 2, which is infinity. So this sucker diverges. You're like, whoa, wait a minute. But it looks as if we should come up with some sort of finite value. Well, it looks as if we should, but when we run the test, we come up with infinity, so it diverges. Now, there is a little bit of a hint here. When we're dealing with positive or negative infinity, problems of this form, from 1 to infinity, where it's 1 over x raised to some power. If the power is greater than 1, it should converge. If the power is less than 1, it should diverge. All right? So converge if it's greater than 1, diverge if it's less than 1. Okay, just for fun, we've been talking about another example, 1 over x squared. We determined that it diverged, but that was when we were dealing with this problem in here in the middle. What if we're only dealing with from here to here? Well, again, let's take this. Our problem is the top. And we take a look at our new rules. We say, okay, 1 over x to the p. P itself is 2 when it's in the bottom, because p is in the bottom. Is 2 bigger than 1? Yes. So we should be looking for converge. Let's see if that works out this way. Well, let's change this into x to the negative second. We still take the limit. Let's go ahead and do the integration. Get negative x to the negative first from 1 to r. Go ahead and plug them in. You end up with a couple negatives. Got to watch your negatives. You end up with a plus 1. But in this case, you end up with negative 1 over, flip the r to the bottom, and it goes to infinity. Well, negative 1 over infinity turns into 0. 0 plus 1 is indeed 1. So we do get a finite value, we converge. So even though when we were dealing in here, we had diverge, when we go toward infinity here, we converge. Even over here, when we were dealing with this inside, it converged, but when we were dealing with the toward infinity, it diverged, even though the graphs themselves look very, very similar. They behave slightly differently. That's why we actually have to run the test. There's a couple key rules. Want to make sure you have that because we'll be dealing with the p-test or comparison test a little bit later. Okay, let's go on to a couple of other examples. Okay, now we have another example, x times e to the x dx, but in this case we're going to be looking from 0 and we're going to go back the other way toward negative infinity. Now, unlike where it blew out this way one way or the other, here this has a defined point at 0, so that's not going to be a problem. However, going to negative infinity is a problem, so I'm going to set up a limit. That limit that I set up is the limit as r goes toward negative infinity. Okay, so all we have to do is integrate. Because to integrate in this particular case, we're going to have to use, wait for it, we're going to have to use integration by parts. So u equals x, dv equals e to the x dx. So we end up with du equals 1, v equals e to the x plus c. So we end up with down minus back, and so we end up with the integral. Well, we end up with x e to the x and minus e to the x dx. Okay, so with that, we could go ahead and integrate, but the problem is we still have this issue because although the bounds no longer apply here because the integration of parts separates them out, we still have this whole limit on the outside. Okay, so with this, we need to begin applying everything we're dealing with. Now, in this case, we're still set up from r to 0. So let's go ahead and integrate this. We come up with the limit as r approaches negative infinity for x e to the x minus e to the x. And we find the whole thing from r to 0. So let's go ahead and plug some stuff in. And we end up with the following. Okay, so let's go ahead and finish this guy up. We replace the problematic bit with a limit. We go ahead and we do the integration by parts. And once we have the integration by parts, we still have to integrate this second bit again. So that turns here, the whole thing is found from r to 0. Now, when we go ahead and attempt to plug that in, we have the limit of 0 e to the 0 minus e to the 0 minus r e to the r minus e to the r. Okay, well this is no big deal. E to the 0, do remember, is 1. So I have 0 times 1, but 0 times 1 is 0. Minus e to the 0, which is minus 1. So I have 0 minus 1. That turns out to be negative 1. Problematic, though, over here, as soon as I start plugging in negative infinity, part of it's no big deal. E to the negative infinity, well, that's 0. Because if we take a look at e to the x, if I go back this way, it's clearly going to 0. So I end up with 0 here. That's no big deal, and it can carry down. So this is coming down, this is coming down, these two are coming down. But when I attempt to plug in negative infinity here, I get negative infinity times e to the negative infinity, so I end up with negative infinity times 0. Uh-oh, indeterminate form. So what I need to do is I need to use, L'Hopital. To use L'Hopital, though, I have to put it to acceptable form, so let's take this, move it to the bottom, and now I have r over e to the negative r, so I have infinity over infinity, because the two negatives will cancel each other out. And so with infinity over infinity as my option, I can derivate the top. A constant goes to 1. The bottom, the negative comes down. And again, minus the negative goes away. So I have negative 1 over infinity. But in either case, that's 0. Plug that in. Negative 1 minus 0 minus 0. All this stuff comes to bear. That's why we have to have integration by parts prior to doing some of the improper integrals. That's part 3.